So to solve the next problem, number 6, we have to consider a curve that is defined as y cubed minus x over y equals 4, and we have to use implicit differentiation to figure out dy dx. So, important to note here with implicit differentiation, we're going to differentiate y under the same rules that we use x, except every time that we do so, we're going to tack on a dy dx. A little example of what that would look like for us is if we said we had d dx of y squared, we would pull the 2 down and do our product rule, or our power rule rather, where we would have 2y, but we tack on that dy dx as a differential operator at the very end. So, doing that, looking at it for our problem here, we'll take out this little bit to save ourselves some room, and we know that we're going to start with this y cubed term. So starting with the y cubed term, if we took the derivative here, and then we take the derivative x over y, and the derivative of 4, we're going to get 3 times y to the 3 minus 1 power, dy dx, like we said a second ago, minus, now we have division here, so because we have division means quotient rule. So for the quotient rule, we're going to take d dx of the top times the bottom minus d dx of the bottom times the top. And we're going to divide all of that by the bottom. On the right-hand side, we're going to have the derivative of 4 is 0. So if we simplify that just a little bit, we're going to get 3y squared dy dx minus y minus dy dx times x over y squared equals to 0. In order to solve this problem, now we need to go and get all of our dy dx's to one side. So all of the things that are not dy dx, such as the term here with just the y, we want to move that to the other side. So I'm going to reorganize so that I have 3y squared dy dx, now plus, because we have a minus sign here and here, dy dx x over y squared. And moving the y part here over y squared over, we'll get a positive 1 over y on the other side. Factoring out our dy dx, we get 3y squared plus x over y squared equals 1 over y. And so the last step is we can just multiply through, or divide through by that last term. So dy dx is equal to 1 over y times 3y squared plus x over y squared. And that's all we have to do for this problem. The next bit for this is number 7. We want to find the volume of a sphere given by 4 over 3 pi r cubed. And we know that r is the radius of the sphere. So we know that r is increasing at a rate of 3 meters per second. So that's going to be a change in r. So we'll say dr. And it's per time unit, so we'll say dt of 3 meters per second. So now we want to determine the rate at which volume is increasing. So if we're looking at a rate for volume, we're looking at the rate of change of volume with respect to time. So in order to find this out, all we're going to do is take a derivative. So we'll take d dt of volume equals to 4 over 3 pi times the derivative of r to the third. On the left side, we get the derivative of volume. On the right side, we get 4 over 3 pi times 3r squared dr dt. Remember earlier in the implicit differentiation, because this dt and this dr are not the same variable, one's an r, one's a t, we have this leftover differential term. We do know, however, from the problem that dr dt is equal to 3. So all we have left to do is plug and chug. 4 over 3 pi times 3 times 2 squared, because r is equal to 2, times 3. And the final answer to that is going to be something along the lines of 151 meters cubed per second, given a little bit of rounding. Depending on what it tells you in the problem, you might round to a couple of decimals. The next problem is taking the top and bottom of a cylinder that will be constructed from square pieces of cardboard, with the excess material being thrown away. So we want to recall that the volume of a cylinder is given to us here, and there are a couple of clues that we need to take away from the top paragraph of information. If we look at the square inches of cardboard that will be used, including the wasted amount, we know that that's 2,400 square inches. So let's make a note of that, saying 2,400 is equal to 2 times, we need the area of the top segment here and the bottom. This 2 coming from the fact that it's just going to be double one or the other. So we can say that that's going to be 2r, and all of that is squared. The reason we have that 2r term is because if we looked at this picture over here, we'd say it would take 1r to get to the top and 1r to get to the bottom. So the entire side length is that 2r. It's 2r squared for the area, because squares are 2r by 2r, side by side. If we take the area of the sides, we've got the 2 pi r, which describes the circumference of the circle, going just on the outside of it, and we multiply that times the height of the cylinder. Just this chunk right here that they put in the picture for us. So now we have this equation that relates our r and our h, and we can solve that for, in this case, I recommend solving for h. It seems a little bit easier. So solving that out for h, we get 2,400 minus 8r squared, all divided by 2 pi r. Taking our v term from earlier for volume, we can plug in for this h and say that we have the volume as pi r squared times 2,400 minus 8r squared, all over 2 pi r. In order to find the value for this, where we have the largest volume, we need to make sure we take a derivative here. So in order to make this easier on us, I would recommend that we go ahead and cancel out a few terms if we can. Notice that we have this pi term that will cancel here, as well as an r term that will cancel here. So our volume equation simplifies nicely to 2,400 r minus 8r cubed, and still divided by 2. We can further simplify that if we wanted to make it just without the division. There. Taking the derivative with respect to r, because since we only have one variable now, we get 1,200 minus 12r squared. Anytime that we want a min or a max, we're going to set our derivative equal to 0. And now we can solve that. We can say r is equal to the square root of 1,200 over 12, or 10. You might notice that I've neglected a negative answer here because we should get a positive or negative 10. But negative 10 radius doesn't really make sense, and so it's omitted. So this tells us the radius that we're looking for.